Okay, so our next speaker in the session is Qianchuan, and he's coming to us from Purdue University. So he's going to tell us about oblivious algebraic data types.
Okay, so I'm very excited to talk about oblivious algebraic data types. First, let me introduce you this mental game called Yaw's Millionaires Problem. So let's say Alice and Bob, two millionaires, want to know who's richer without disclosing their actual wealth. So in other words, they want to compute something together, in this case, a Boolean indicating who's richer, and they want to do so without disclosing their private input. So like in this case, how much they have made. This is an important problem in cryptography, as it formally introduces secure multi-party computation, or in this talk, we call it oblivious computation, that allows multiple parties to jointly compute something without leaking the sensitive data. So, well, at least not more than what you can infer from the output. So this is not just a mental game. One application, for example, is that multiple hospitals may want to compute the statistics of their patients' data, but they may not want to just simply pull the data and then compute the result because, well, I mean, it may not even be legal. So for these kind of applications, multi-party computation or secure or oblivious computation is a very powerful tool. In fact, cryptographers had already provided solutions to this problem. However, most cryptographic protocols require the computations to be encoded as some sort of circuits. So it's not really viable for the more complex real-world applications. And so with recent efforts in the PL community, we can write such applications in a high-level programming language, and I list some notable ones here. They try to tackle this problem in different angles, but what's missing, or what we are trying to do here, is to support rich recursive data structures like trees. And I'm not talking about data structures with only private payload, but data structures whose shapes are also private. And we call these oblivious algebraic data types that basically have private payload and also private structures. For example, an attacker should not be able to tell if an oblivious tree is left heavy or right heavy. So this is useful in, for example, private decision trees and other applications with private data that is naturally represented as some sort of recursive data structures. So in this kind of applications, an attacker is one of the participants running the program, so they are very powerful. They can see the data in memory and they can see how the data is used. And being able to see the data in memory, basically it means it's not possible to have a completely oblivious recursive data. For example, let's say we represent a password as a list of characters. Even if all the characters are encrypted, we can still infer that this password is 3 characters long if we are not being careful. And in general, the attackers can always infer some approximate bound on how big this data could be by just looking at how much memory it uses. So the best thing we can do here is to ask the participants to agree on a public view as a compromise. And a public view is essentially some sort of upper bound on the shape of the data. For example, the public view of list could be the upper bound of its length. So in this password example, let's say everyone agrees that their passwords are not longer than 16. Then all the passwords will be padded to this upper bound to obfuscate the shape of the data. And of course, list is just like a simple algebraic data types. For the richer ones like trees, the upper bound, or I mean the public view could be the maximum height of the tree, for example. And on the other hand, like I said, the attacker can observe the whole execution, including every program state, meaning that even if all the data is perfectly obfuscated, they can still infer some like private structural information by looking at the side channels, like timing channel or control flow channel. For example, let's say we want to sum up all the nodes of a tree and assume everything here is encrypted. But as soon as this program takes the first branch, we immediately know that this tree is a node, not a leaf. So to summarize what we are trying to do here and what we have indeed achieved in the paper, We want to allow the programmers to define data types with whatever public views they want. And of course, we want to make sure no private information is revealed throughout the whole computation. And lastly, we also want to separate the program logic and the security concerns. In this case, I mean what public views we use. I will talk more on that later. So as the first approximation, I will introduce this core calculus called lambda OADT. I will be using this binary search tree as a running example. So the tree is defined in a standard way with bounded integer payload, and the local function takes a search key and a tree and returns if this key is in the tree. So very straightforward. So in lambda OADT, we can define a corresponding oblivious tree head this way, and we use head to kind of like indicates this is an oblivious type or oblivious operations, but it has no significance in the syntax, just like a visual cue. So we defined this tree head as a dependent type, with the type index being the public view. And in this case, the public view k is the tree depth or maximum height of the tree. So if k is 0, apparently the tree can only be a leaf. So we return a unit type, which is isomorphic to a leaf. Otherwise, it could be a leaf, it could be a node, and well, this part is isomorphic to a node. And apparently, you also need to pass the correct public views to the recursive calls. And we connect them using oblivious sum, which is basically similar to normal sum, but the tag and the payload will be obfuscated. So you won't be able to tell if it's left injection or right injection. And you may also notice that this is essentially a form of large elimination because we kind of just compute the type by eliminating the public view, which is the term argument. Here is an example of an oblivious tree of public view 2. So this type will be computed to the type normal form on the right-hand side, which roughly corresponds to this complete tree. And the key here is all the trees or all the data in this type will have this exact same shape. So the attackers cannot glean any information by looking at the shape of this data, this type. Of course, we can also define another oblivious tree with a different public view. In this case, we can use the upper bound of the spine, which is basically a tree without payload. So by choosing different public views, essentially we are making trade-off between performance and how much information we are willing to give away. In this case, by using the upper bound of the spine, we have less padding because we don't need a complete tree anymore, and hence less wasted computation. And we also need some oblivious operations to protect against the control flow channel. So this is the mux operation, and I will only introduce this one, but this is not something new. You can find it in other oblivious languages. So in this case, I use these box numbers for oblivious values. You can think of them as encrypted values, encrypted numbers. So mux takes an oblivious condition and oblivious branches, and it behaves kind of like a if conditional, but if you fully evaluate the condition and all the branches first before taking the last atomic step to the final result, even though one of the branches will be discarded anyway. So this always generates the same execution trace regardless of the value of the condition. For example, if we change the condition a little bit, now it returns a false. The trace will still be the same, given that the attackers cannot observe encrypted values. And aside from dependent types for writing oblivious data types, the type system of lambda OADT also makes sure you don't do anything funny to break the security guarantee. Now you can write an oblivious local function this way. You don't have to read the code. You probably don't want to write anyway. This is too much work for a simple local function. But basically, you need to, the program needs to take another an actual argument for public view. And you also need to pass the right public views to the recursive calls. And before you can access any private data, you need to follow the definition of the oblivious tree and eliminate the public view accordingly. And you also need to use some trick to make the dependent type checkers happy. So that's not great. This program contains a lot of boilerplate, and basically it obscures the original program logic. But what's worse is that if we want to use another public view, we need to write another version of the local function and deal with different boilerplates, even though the high-level program logic is exactly the same. So ideally, we want to just like write this public program, right? Like write this plain text program, like how we always do it. And when we need an oblivious version or secure version, it would be great that we can just simply lift this public program to the secure version. And to do that, we can first decrypt the private input and then apply the public function to it, and eventually encrypt the output back to the original, back to the oblivious world. This should give you an equivalent program. And in this diagram, the S and R here stands for section and retraction. So section roughly corresponds to encryption, and retraction roughly corresponds to decryption. So the appeal of this approach is that you only, as a user, you only need to provide a section and retraction function for a particular public view once and for all. And then we can just like lift whatever public functions to the oblivious world. And it also separates the program logic and what public views you decided to use. But there's one tiny problem. It's not really secure, because as soon as you decrypt the private input, apparently you just release whatever, all the information you care about. But the good news is you can't even write it in Lambda OADT. But to support this paradigm, we extend Lambda OADT and proposed this core calculus called Lambda OADT with tape. So the idea is to have the semantics to repair or tape up the potential leaks for us. And before I tell you how that works, first we need a mechanism to define retraction functions, because you can't actually do it in Lambda OADT just yet. So this is called a leaky conditional. It's kind of like a mux. It takes an oblivious condition, but it also allows public branches. So you can use it to express these retraction functions or decryption functions. But apparently, if you actually run it naively, then it would just like reveal the private condition. So to maintain this security guarantee, the first ingredient to Lambda OADT with tape is to observe that this program only leaks if we actually run it. So the solution is simple. We just don't run it. And more specifically, this leaky condition is considered as some sort of some special kind of value. So it's not reducible. But now we have another problem. The program could get stuck if you use it in a larger context. In this case, the condition is not in a canonical form, so we don't know how to keep going. But the second ingredient is to observe that we can still make progress by distributing the surrounding context into the branches of the leaky conditional. So in this case, we kind of like push this if context into the branches. And now we can make more progress. And you may notice that this if context is executed in both branches, which is actually aligned with how what Oblivious computation will do to protect against a control flow channel. And the third ingredient is this table expression that kind of defines the boundary of the potential leaks. So the key is the expression in tape needs to be eventually oblivious. So in this case, if you naively run the program, the result should be encrypted 5, which is oblivious. And here's how it works. So first, observe the branches of the leaking conditional are public at the moment. And we start by pushing this if context into the branches. And now do more reduction. And now the branches become oblivious. So we can reduce the whole thing into a mux and finish the computation securely. So I hope this is intuitive that throughout the whole execution, there's no private information actually revealed. The actual semantics is slightly more complicated, but this is the idea. And this strategy also works for other leaky expressions that we use to write retraction functions, like the leaky case and the primitive retraction function for bound integer. And our type system will make sure you use the tape correctly. All right, so with all these ingredients and a few more ingredients that I didn't talk about, we can put everything together. And first, we define this oblivious tree, and then we define a section function that converts a public tree to an oblivious one, which roughly corresponds to encrypting a tree. Don't mind the notation here. You can learn more in the paper. And we also need to write a retraction function that does the opposite. So it roughly corresponds to decrypting a tree. You do have to deal with the boilerplates and the dependent type stuff here, but you only do it once and for all. And once you have all these functions at hand, we can simply lift the original public function to an oblivious version by composing it with these section and retraction functions. And if you want to use a different public view, it's as simple as replacing that oblivious tree and section and retraction functions accordingly. So compared to the previous approach, well, it doesn't seem like a lot of improvement in terms of lines of code in this particular simple example. But the key is the local function is defined in this standard functional programming language. So that's because the public fragment of lambda OEDT with tape is just conventional. So the programmers writing this program don't need to know anything about cryptography or dependent types. They can just write it like how they always do it. This makes the programs much easier to write, much more readable, and also much easier to reason about. I'm not going to dive into formalization and proofs, but we have formalized these two calculi, and we have proved the soundness and obliviousness theorem, which is essentially some sort of non-interference theorem. I'm not going to explain the statement here, but basically it justifies that our system is indeed free of leakage. You can learn more in the paper and also check out our Coq formalization. You're also welcome to come to my Coq PL talk on Saturday, where I will be talking about how you can generate some boilerplate definitions and lemmas and how that applies to our formalization. So to recap, we introduced lambda OEDT with dependent types for defining oblivious types with public views. It has oblivious operations and also a type system to make sure the security. And we introduced lambda OEDT with tape that features some leaky expressions for writing these decryption or retraction functions. And the tape semantics and the type system will make sure the private information is still protected. And from the user's perspective, you only need to write this oblivious type and the corresponding section and retraction functions once and for all, and then just write your program like how you always do it. And then eventually you lift your programs to the oblivious world, and then enjoy the security guarantee we have proved. You can also just use different public views or compare different public views easily. So with that said, thank you for your attention, and I'm happy to take any questions.
Okay, we have some time for some questions. I will say that the online crowd just loved your talk. Lots of good reactions there. So let me get a question here.
Hi, this is Mike Hicks, University of Maryland. I wonder, would there be challenges in adding references and mutation to your language?
At the moment, we haven't considered that yet. And I'm not sure how hard it would be to add a reference and other like side effects, but that's definitely something that is interesting and we will explore in the future.
More questions?
Hi, I'm Jed Gallieni from the University of Cambridge. So I know we have to have the runtime be constant based on the dependent type to avoid leaking information. So are there any further techniques explored to like reduce the runtime? Like, for example, I don't know, parameterizing the tree based on the size and like flattening it, or like using a size function and flattening, for example. So
Yeah.
you'd have linear time rather than exponential.
Yeah, that's a very good question. We have not explored the optimization techniques at the moment, but indeed, if you want to have this strong security guarantee, basically you have to traverse the whole tree in most cases. One particular optimization technique that we have been thinking about is kind of like you can align the computation in different branches, and if they are like doing similar things but with different private payload or private arguments, you can kind of like collapse them by first merging those private argument first and whatnot. But we have not like done a lot of work on that space yet.
Sarah. Okay, we have an online question. Okay, so this question is from Jesse Grossen. How would these operational semantics, particularly of the taping, actually be implemented with MPC?
That's a very good question. So this work currently focuses more on the theoretical side of it. So we do not actually have an implementation yet. So I can't really say anything for sure at the moment. Yeah, but that's what we will be exploring later.
Okay, let's thank Qianchuan again.
Thank you.